Good morning, everyone. I am Avinaya Tripathi. I am doing major focus of my research in 3D printing of concrete. I work with Professor Narayan Nethalat at Arizona State University. So I'll be presenting about like how we can create like composite sections that could give us the mechanical strength that a UHPC gives you while still getting like less costlier and more sustainable prints. So starting with 3D printing, like everybody has told, no use of formwork, the architectural freedom to create different kind of weird sections, layer-wise construction, giving you freedom to like use multiple kind of system, 1K, 2K, all those things. With all those advantages, people are like moving into 3D printing more and more. So we at Arizona State University have a gantry printer that's like 1.8 by 1.8 by about a 1.8 meter height volume that we can print. So as the start, like we had to create a UHPC mix that's printable. Like for the shortness of the presentation, I'm not gonna give you the detail of what kind of mixes we made, but we tried out different mixes, different binary, ternary formulations to reach at a certain mix where we have like a 60% by mass of binder, and a 40% by mass of aggregate. And aggregate is like just medium sand, quicker medium sand of 0.6 mm particle size. So we have in the binder system, we have 70% of cement with 10% of fly ash, limestone, and slag each. So it's like a 70 cement versus 30 replacement agent. So for this to be printable, like in a cast system, you could put in more SP into the mix and you can make the UHPC flowable and you can just cast it. But in printing, we need the mix such that it's flowable enough while you are pumping it or like when you are extruding it, but it needs to be stiff at the moment it leaves the nozzle, it needs to be stiff. So to do that, we tried with different superplasticizer percent without changing anything else. So when the mix was like flowable but buildable at around 1.1% SP content on the mix, and we did not change the SP percentage with fiber. Yeah, with additional of fiber, you'll get the mix a little bit stiffer, but still we had extrudable mix. So we just added like 1% of steel fiber and 1.5% by volume of steel fiber. The steel fiber here is a Baker fiber that's 13 mm in length and 0.2 mm in diameter. So shown below on the two pictures are the buildability test for these mixes. It's done just after 15 minutes of mixing. So for walls elements that's shown on the right of thickness 25 mm, we could go up to like 31, 32 centimeters after 15 minutes of the mixing. And for cylinder kind of elements, which has a 7 cm inner diameter and 12 cm outer diameter, which reached around like a meter height without any failure. Like we did not go beyond the meter. So these mixes are printable and buildable. So for compression tests, we created large slabs of which we cut like cubes and we tested all three directions. We made a representative cast sample as well as a print sample. So shown in the figure from left to right are the UV. Basically, I'm going to refer to them as UV, UVSF 1% and UVSF 1.5% based on the fiber volume percentage. So on the left is a UV and it goes to 1%, 1.5% on the right. So what we observed during this is that these mixtures, because of the rheological modification that we are still getting like similar strength in the printed sample when compared to a cast sample. That was the first observation. Second observation, major observation was that the anisotropy that we see in 3D printed elements, that's nearly not present in these samples. I'll show you based on a calculation we have that when I say direction 1, it's going to be like the compression along print direction. Direction 2 is along the filament direction, and the direction 3 is along the build-up direction. So another thing we have here is like we have multiple filaments on the same system. Because what we have observed is like, let's say if you have just a single filament of the total width being there, you will not see the interfilament effect. And interfilament effect is quite significant in printed elements, as we have observed in like a normal strength as well as UHPC mixers. So based on these strength values, we wanted to see what the anisotropy in these elements were and why is it so. So on the left, you see a anisotropy coefficient calculated based on the 3-directional strength test. You can see for UB at like 28 days, we are in the range of 0.03 anisotropy coefficient. For even with steel fibers, we are like within like 0.1 at 28 days. In comparison to a normal strength mix, that's like a 70 MPa mix we use for our work in printing. We had an anisotropy coefficient of 0.4 in those samples when we did similar layer height, similar filament width printing, and we did like 3-directional test. We were in the range of 0.4. So we have a significant reduction on the anisotropy. Now, why is it so? So based on a microscopy image, we saw the top two shows a microscopy image for the UB mixer, while the bottom two images on the middle shows a microscopy image for a L30 mix. That's our 70 MPa mix. So what did we observe? There were two major observations from the microscopy image. One, like the lines that you see in the images that go kind of horizontal are the interlayer joints, and the dotted line you see that goes vertical are like the interfilament joints. So if you see the UV mixtures, you will not really see actual voids, large voids that are significant enough. But if you see the L30 mixture, we can see those significant void being formed along the interfilament and interlayer joints. Why does it happen like that? So UV mixture, because of that high SP content, you will see that the mix flows till it's like sits on the filament. So it has the capacity to flow into these voids, rather not creating the voids, but filling up the interfilament and interlayer joints. While for a stiffer L30 mixture, because the shape you place will be the shape you get, and there might be sometimes like air bubbles kind of, not air bubbles, but again there might be voids forming on those joints, so they kind of exist in the sample. So that was one of the observations we saw with this UV mixers, the UHPC mixers for compression. On flexure, how do they perform on flexure now? So in compression, we saw that the casted sample and the printed sample had like similar compressive strength, but we see that for the UV mixer shown on the left, we have about a 40 to 50% loss on the flexural strength when compared to a cast versus a print. So everything labeled by C dash represents the cast samples, and everything labeled by P dash at the initial represents a printed sample. So we see that there's a significant loss of flexural strength. Why does it happen? Now, these smaller voids that are present in the print, despite like the flowability being maintained, the rheology being maintained, there are still some voids being formed which are significant when there's a tensile load rather than a compression, because under compression they will usually have a closing effect, while in this they will have a stress concentration effect. So that's there. But with the use of fibers, we saw a significant improvement rather than deterioration, because I'll talk about the reasonings in the next slide also, but now in printing what happens is like these samples are tested so that the length direction of the span of the beam is along the print direction. Now the span being along the print direction, we see that the fibers are also oriented along that direction in printed samples because of the characteristic flow of these mixes. So we see that at 1%, the lower two black and green graph that we see there, the one represented black is the cast sample for 1% steel fiber, while the green one is for the printed ones. So we see like there's a increase in the strength in the printed sample compared to cast, because in cast you'll have more of random oriented fibers, while in print you have like more of aligned fibers. But at 1.5% we see that those two are more or less same. Now, why does that happen? Again, these are the flexure strength based on the sample. We see like high DIC, from DIC we see high strength concentration during the peak load, we have like more ductility. But why does the strength happen like that between the cast and the printed? So we see again cut cross sections out of our print sample versus a cast sample, and we took again another microscopic image to see how the fibers are oriented along the print direction, how the cross sectional image are. So the top two are like basically a transfer section cut along the length print direction or length direction of the beam. You see like at sections the fiber are mostly directed along the length of the beam. If you cut a cross section that's perpendicular, like basically a cross section of the beam or perpendicular to the length direction, you'll see there will be like circular kind of fibers being shown in the cross section, because now this shows that the fibers are more oriented towards the length direction. But if you see the fourth image D, it's for a cast sample, if you cut a random section, be it along the length of the beam, be it perpendicular to beam, you will see like some circular, some elongated, some weird shape kind of steel fibers because they are randomly oriented. There's no particular orientation to it. So this basically tells us why the 1% perform better. But why did it 1.5% not perform as better compared to a C? Because there should be fiber orientation in those also. So when we saw the cross-section image along the interlayered joint of the beams, what we observed on the figure that you see on the right is like, because the system are such that we only used 1.1% SP and we just kept on adding the steel fiber. So with high volume percentage of steel fiber being added on, the mix gets stiffer and stiffer. So at 1.5%, we saw that along the interlayer joints, though there was no void initially, for these samples there are voids. So somehow this void formation and the fiber alignment are cancelling each other out, and that's why we see like the casted sample perform as well comparative to the printed sample. So that was our observation from flexure. So the slide did not change. Okay, so based on this, I'm just going to move into the slides. I changed it, but I think the modifications are not there. So why now we got the increase in the strength, right? Why not use a UHPC mixers? What is the detriment in using systems like this? Why are we not going for it? So to see that, we need a proper life cycle analysis of this mixes. So what we did is like for the L30 mix that I talked about before, that's like basically a 30% limestone, 70% cement, 50-50 binder and aggregate. For that mix, which is a normal strength, and the UHPC mix, we did a life cycle analysis from cradle to gate basically. So from initiation to mix phase. So when we did that, we see like for all different mixes, we calculated the carbon dioxide emission and energy demand that we have for these mixes. So these are basically I'll go to the top table only for initially because those are the three mixes we are comparing, and we see like the cost significantly for these mixes because it's a low water cement ratio mix, high cement content being used. The cost itself with those fibers and everything coming in, it's like 4-5 times more than compared to a L30 mix. And carbon dioxide emission is 30-40% more than a L30 mix. Yeah, we are getting like 5 to 6 times the flexural strength for these mixes, but we are still getting higher cost and higher carbon dioxide emission. To come back to it now, what is the solution to it? What can we do? Now 3D printing allows you to do layer-wise construction. Why not create the higher cost, higher mechanical property strength mixes along the places you need it and replace the ones that you don't need with lower strength, lower cost, lower carbon dioxide emission mix. So we tested different cross-sectional prints, but for the sake of being shorter, I'll talk about two sections that we printed. One is with the L30 mix, that's the non-fiber L30 mix, substituting the top half of the beam. And here's a slab, we'll cut beams out of it, so I'm just going to refer to it as half of a beam. So top half is replaced by a L30 and bottom half is a UHPC mix, and top half is a L30 and bottom half is a UHPC mix with that 1.5% steel fiber that we saw before. So what happens as a response to when compared to this? For the non-fibered ones, we saw near similar peak load performance for the composite sections. The significant observation now comes when you are using a steel fiber mix that's shown on the right hand side. So the blue line on the top is a homogeneous beam. You have the UBSF 1.5% there. So everything has a steel fiber from bottom to top. But the green line that you see has like from bottom to the half of the beam there's steel fiber, while from half to the top there's no steel fiber. It's a L30 mix now. So technically you have half the volume of steel fiber being used, but if you see the ductility is lost because of the reduction of steel fiber, but you are still getting like just 15 to 20% decrease on the overall capacity of the load carrying capacity of the beam. So we'll talk about it more in terms of the life cycle of these things, but this is a significant improvement in the sense of like there might be a deterioration, but we will come into it in the next slide that now we'll get a significant cost reduction and carbon dioxide emission reduction because of this sections. We tested for the opposite section also where we put L30 on the bottom and then put SF on the top because there might be sometimes a negative moment coming in. The L30 not having a fiber kind of breaks, and this more or less acts as like a reduced section where, let's say the beam size is a 60 mm that I'm using. So the response will be equivalent to a 30 mm UHPC SF 1.5% beam that we have. So based on that, we calculated or used the transform section method to see if like the carrying capacity is an effect of print also, from which we saw that it's not exactly a effect of the mixture getting more strength or anything. It's just basically a combined effect of these different moduli mixes acting together. So when we calculated based on transport section method, we see that the strength of the beam on the, basically we calculated the flexural stress that's at failure at the extreme fiber of the beam. We see that the strength is basically nearly similar to the mix that's in the extreme fiber. So if you have a UV SF 1.5% at the extreme fiber, you will see like the peak strength on the composite beam also is similar to the, nearly similar to the homogeneous beam's strength. So based on this, when we did the carbon dioxide and cost emission for these mixes, from the top table, that's a homogeneous beam versus the bottom, that's a composite beam. Here the AM modified means like, I showed you results for three layers. That's basically a half of the beam. The modified AM represents 2/3 of the beam being replaced. Like, why don't we replace more of the UHPC mix with the L30? Because towards the compression side, we don't need that much of the strength, right? So these are comparative values for like a half of the section and 2/3 of the section being replaced. So we see there's like a cost reduction of around 40% on the fiber CSM. If you see that, that's around $300 kind of thing from a 540. The thing we should remember is like it's just a 15 to 20% loss on the strength. While we see for carbon dioxide, we are getting another 20-30% decrease on the carbon dioxide emission. Now, how does this correlate to when you actually have to design? To show that, what we did was like we designed a 6-meter long beam to carry a 3 kilonewton per meter load, UDL load. And keeping the width constant at 200 mm, we are just varying the depth to see what depth is required to carry that load. And based on that cross section, we are calculating the volume, and then we are correlating that volume to how much material cost we have for the section and how much carbon dioxide do we have because of that section. And how does that correlate from the homogeneous beam to the composite beam? If you see the top L30 mix, we are comparing everything on the right two columns based on that L30 mix. So that's why it has a 0% difference. But when you come to UVSF 1.5%, we see that there's a near 30% more cost for this section, while CO2 emission is still 33% less. When you see the section CO2 emission directly, we saw that it was like 30% more, right? But because of that 6 times strength gain, we actually get a carbon dioxide reduction because of the UHPC SF 1.5% mix itself. Now, coming to the composite section, the lower one, CSF and CSFM, we see that further we get at the total, when we are replacing it, we are getting in the range of 22% reduction in the cost, as well as a 45% reduction on the carbon dioxide emission. So this shows like, okay, you could move on to take the advantage of layering system, where you can put different materials in different layer to get more beneficial, more cost effective, and more sustainable kind of sections out of this. How would this not be possible in a cast system? Because in cast system, you will have like cold zone kind of effects when you are trying to create 2 different mixes if you wait long enough. And if you don't wait long enough, you'll have a intermixing, because you'll have to basically dry rod or vibrate it. You'll have an intermixing effect, and you might not get as significant of a contribution that we are seeing here. So with that, I'd like to conclude my presentation by acknowledging ASU, my advisor, Professor Narayan Nethilath, NSF and US Department of Energy for the funding, and my senior Suraj Nair, with whom all this research have started at. Any questions?